Okay, I want to look at a couple problems that are actually related to this week's test. So this one is from chapter 4, number 17. Okay, so they have a person fishing from a bridge. Okay, they tell you that the line will break when it exceeds 42 newtons. All right, and they want to know what's the weight of the heaviest fish that can be pulled up vertically. Okay, when in part A, it's being pulled up at constant speed. Okay, so here's the picture. So the person's up here. Okay, so here's the fishing line. Here's the fish, like that. Okay, there's the fish. Okay, and they tell me it's being pulled up at constant speed. So that's reflected in my diagram. So speed is constant. Okay, speed is constant. That means the acceleration is 0. So for part A, acceleration is 0. Okay, and they want to find the weight of the heaviest fish. Okay, so that's a force problem. So I have my picture, have my forces on the fish, the tension, the weight of the fish. Picture forces, coordinate system. Well, it's not accelerating, so I just picked a regular coordinate system. Nothing to break up, and so I applied F equal ma to the fish in the y direction. Okay, acceleration 0. Okay, so I look at the picture, tension points up, mg points down, that's equal to 0. So I'm solving for the weight of the fish. I'm solving for mg. So that says mg is t. Well, the maximum tension that the string can have without breaking is 42 newtons. That's the maximum weight of the fish. Okay, so that's about 10 pounds. Now, part B, they say, okay, instead of pulling it up at constant speed, you want to yank it up quickly. Okay, so you're going to accelerate it. So if you want to yank it up quickly, then that means you're going to have to sacrifice some weight, so the fish can't be 10 pounds, it's going to be lighter than that. So they want you to find how big will that fish be if you decide to accelerate it at that rate. So for part B, okay, my acceleration's upward, so my coordinate system's still okay. All right, so again, I want to find the weight of the fish. So for part B, I'm looking for mg, okay, the weight of the fish. Okay, so I did F equal ma to the fish in the y direction. Tension points up, mg points down. That's equal to ma. Now I want to solve this for mg, but I don't know m. So I'm going to solve this for m first. Okay, so I brought this over, did the algebra, factored out the m here, factored out m. Okay, now the tension, okay, so the biggest tension the string can have is 42 newtons. That's what I put there, 42 newtons. And I put, that's the acceleration of the fish, that's g. So that gives me the mass of the fish, but they want the weight of the fish. So I had to do mass times gravity. That gives me the weight of the fish. So with that fishing line, you can pull a 10-pound fish up at constant speed, but if you want to do it quickly and accelerate it, the fish can only be about 8 pounds. Okay, so that's the number they're looking for. Okay, okay, number 26, all right. This problem is going to remind you of the jet car problem, where the jet car skidded on the desert salt bed. So here they give you a skater, give you the initial speed, okay, and then they're at rest. And so I drew the skater moving here, okay, and they eventually come to rest because there's a friction force. Okay, you have the force of kinetic friction. So for part A, they give you mu sub k, that's mu sub k. They want you to find the deceleration. Okay, now they didn't have to call it deceleration, they could have called it acceleration. Okay, whether you're slowing down or speeding up, you're still accelerating. Okay, but if you're speeding up, you wouldn't call it a deceleration. So deceleration usually refers to you're slowing down. Okay, so the bottom line is for part A, they want you to find the acceleration. So here's the picture of the person moving. So in my picture, I clarified that they're moving to the right, okay, but they're slowing down. Speed is decreasing, so acceleration points backwards to the left, okay? So that dictates my coordinate system, right? The acceleration has to be negative, it doesn't have to be, but you should make it negative when it's slowing down, okay? So, whoops, that picture's not right. Let me fix that. Like that. Okay, so acceleration is negative because it points to the left. Okay, so here they're moving, okay? So I want to find acceleration. That's a Newton's law problem, so 5-step method. Picture, drew the forces on the skater. Normal force, mg, They're moving to the right. Kinetic friction, okay, that's a retarding force, so it points to the left. Okay, it's trying to slow them down, trying to prevent them from speeding up. Nothing to break up, okay? And then I apply step 5, F equals ma in the x direction, because I'm trying to find A, and A points horizontally in the x along the x-axis. Okay, so I did F equal ma to the skater. Okay, look at the picture. The only force I have is kinetic friction. It points backwards. That's why it's minus. Okay, so I have minus F sub k equals ma. Okay, but remember in this chapter, the kinetic friction force is always mu sub k times n. But I don't know n. So I had to do F equal ma to the skater in the y direction. So n points up, mg points down. That's equal to 0. So normal force is just mg. So right here I have F sub k is mu sub k n. N is mg, so I put that right there. So I call this equation 2, and then I said substitute equation 2 into number 1. So take this number 2 and put it right there. So right here where I have F sub k, I'm putting in mu sub k mg. So right here where I have F sub k, I'm putting in mu sub k mg. That's equal to ma. All right, so the m's cancel out, and that gives you my acceleration. They give mu sub k, and you know g. Right, it makes sense that it's a negative. It's slowing down. All right. So part B, they want to know how far will it go. Okay. So that's my delta x. That's my whole delta x in this whole picture from there to there. That's my delta x. Okay. Whoops. Okay, so for part B, right? So the pattern is you can apply F equal ma, but there's no delta x in F equals ma, so that's why it's a kinematics problem. So I look at the picture and I have a V initial, I have a V final, and I want a delta x. That reminds me of equation number 3. That's equation number 3. So V final 0, solve this for delta x, and I have everything in here. I have V initial, and I have A, that was from the first part. So that's what I did here. I put in my V initial, put in my A, and that tells me how far they slide. Okay, now that's done. Okay, now in the next chapters, okay, in the energy chapters, okay, we have this expression that the only way the energy can change is if there's a non-conservative force that comes by and causes it to change. It does work. So change in energy is final minus initial. So I took the E initial, brought it over to make it positive, to make life easy. That way I don't have that negative sign. Okay, and then I have to ask, okay, well, are there any non-conservative forces that do work? Okay, yeah, I have kinetic friction force does work. Okay, so that kinetic friction force points backwards. Okay, so remember to find the work done by a force, it's the force times that distance to which the object moves, times the cosine of the angle between them. Remember, friction points backwards, the skater's moving to the right, and the angle between those two arrows, or those two forces, 180 degrees, and cosine 180 is minus 1. So the work done by the non-conservative kinetic friction force is that. So it's minus F sub k times delta x. So I went back to here. Okay, my E final is kinetic plus potential, E initial, kinetic plus potential. Now everything's horizontal. Okay, so when something is horizontal, I don't need to worry about potential energy. It's not changing. So essentially, back in my picture there's the skater. I took potential energy to be 0 on the ground. So initial potential 0, final potential 0. Okay, so final kinetic is 0 because they're at rest. Okay, they come to rest. Initial kinetic energy, 1/2 mv squared. And then work done by non-conservative forces, that was this thing. So here's my 1/2 mv squared. Okay, I brought this thing over. Okay, now it becomes positive. And remember, kinetic friction is always mu sub k times the normal force. Normal force is mg. And then right here I put in for my kinetic friction force, masses drop out, and that gives me my delta x. And that's the exact same thing we have above. Right up here. Because A is minus mu sub kg. So here I have this A, I have that, and if I took that and put it there, the minus signs would cancel, and I have V0 squared on the top, and 2 mu sub kg. That's what I have right here. V0 squared on the top, 2 mu sub kg. Okay, and it shouldn't be any big surprise because in the energy chapter in the notes, we used Newton's second law and the kinematic equation number 3 to come up with that whole expression. Okay, so we just did the skater problem. Okay, right after that is 2 problems I want to look at that are related to the chapters we're doing for our second test. Okay, so here I have a car driven at constant speed. Okay, so cruise control is set. And here it goes over a hill, and then, and then over here, okay, it goes downhill. Okay, it goes through a dip at the same speed. So the speed is the same in both pictures. So I called this picture 1, and I call this picture 2. Okay, and they say the driver is sitting on a scale. So at the top of the hill, I drew the driver over here. Okay, and I drew this little scale. The blue thing right there, that's the scale. Okay, so they're sitting on the scale. And it says at the top of the hill, the driver notices the scale reads 27% of their weight. Okay, so for example, if they weigh 100 pounds standing on a scale at home, they would look at the scale would read 27 pounds. They feel lighter. All right, and we saw in class, or we saw when we did these notes, that if you went a little bit faster, you could actually be weightless at the top. Okay, but here they're 27% of their weight. And given the mass of the driver, what does the scale read now when they're at the bottom? Okay, at the bottom of that dip. Okay, so I'm trying to find what is the scale read here. So essentially they're asking, what is the normal force? N equals what? Right there. Okay, and if I call this one number 1 and number 2, I want to know what is the normal force when they're here at the bottom. Okay, so when they're here at the bottom, I drew the picture. Here's them at the bottom of the dip. That's the person, okay, of mass M. All right, they're sitting on the scale. That's the blue scale. So I drew the forces on them. Okay, so 5-step method. Picture, forces. Okay, so I have their weight. Weight points down. Normal force points up. This is picture 2, so I call that N2. All right, they're accelerating toward the center. Okay, so again, I don't have to draw an X and Y axis because I'm going to do net force centripetal equals MA centripetal. Okay, nothing to break up for step 4. Okay, so I want to find normal force number 2. Okay, but now, so essentially what the problem says is, okay, driver sitting on a scale. At the top, the scale reads 27%. Okay, so remember, the normal force is what a scale would read. Okay, so if the scale reads 27% of their weight, okay, and the scale reads the normal force, okay, and just posing the problem, they tell you that the normal force in picture 1, okay, is 27% of your weight. So the normal force is 0.27 mg. Okay, you feel 27% or 0.27 of your weight. So if the scale reads 27% your weight at the top, what percent does it read at the bottom? Okay, so I want to find this N2. N2 equals what? Okay, so I'm applying F equal MA in the centripetal direction for picture number 2. So normal force points up, mg points down, that's equal to mv squared over r. So I'm solving for N2. Okay, so I have their mass, have the radius, but I don't know v. I don't know the speed. So now I have to do F equal MA to picture number 1. Okay, so I go to picture number 1, picture number 1, okay, and I want to do Newton's second law. So I drew the forces on the person. Normal force points up, mg points down. Remember, they're in circular motion, so they're accelerating toward the center. Okay, so picture forces, coordinate system is based on A, okay, nothing to break up. So I'm going to do F equal MA for picture number 1. Picture number 1. Okay, so mg points positive, normal force points upward, that's a negative direction. That's equal to mv squared over r. Remember, in the problem it said the speed is the same. It's going at constant speed. So I don't have a v1 and a v2. okay? All right, and oops, I call this is N1, okay? But the normal force for picture 1 is 27% their weight, so 0.27 mg. So right there, I put in, that's my N1, 0.27 mg. So mg minus N1, mg minus N1, okay? And this is 1 mg, so 1 minus 0.27 is 0.73, okay? Mass drops out, okay? And I could solve that for v, but I'm going to leave it as v squared because that's what I have right here, is I have a v squared, okay? So right where I have my v squared right there, I'm going to put in that. So I said substitute b back into equation A. Okay. So there's B. This is equation A. So mg plus m. This whole thing is v squared over r. So the r's cancel. And I have 1 plus 0.73. Okay. So that's what I was trying to find. So at the for this ride, if they feel 27% their weight on the top, they feel lighter at the top. They feel heavier at the bottom. Okay. They feel 73% heavier. So even though I did this for drawing forces on the person, I could have drawn forces on the car. Okay. If your backpack was sitting on a seat next to you, I could have drawn the force on the backpack. So everything in every person in the car feels 73% heavier. Okay, so if the person weighed 100 pounds, okay, scale would read 27 pounds here. Scale would read 173 pounds over there. Okay, so they want to find, whoops, where's the question? What does the scale read? Okay, the scale reads the normal force. So the scale reads 1.73 mg. So that's what the scale would read. Okay, here's another problem. Okay, so I have this puck going around a circle, goes around a circle like that. Okay, so you could stand here, okay, and maybe swing it around the circle. Okay, so this is frictionless. So somehow it got put into a circle, and the thing that keeps it going in a circle is you have this other heavier weight here, okay, to provide tension in the string. So this one's little m, that one's big M. Okay, so you're given the mass of the cylinders. Okay, the diameter of the circle. Okay, so careful, they give you the diameter. So that's the radius in meters. Okay, and it says use the 5-step method. That's a hint. Use a 5-step method to calculate the number of revolutions per minute necessary to keep this big cylinder at rest. So if this thing slows down, let's say if there was friction, there's not friction, but if this thing slowed down, then this thing wouldn't be moving fast enough to provide the tension, to provide a tension force. So this large mass would fall to the floor. So I want to find the minimum number of revolutions per minute that this thing has to have, okay, so it keeps enough tension for the large mass not to fall. Okay, so we saw that in the circular motion section, that when they say revolutions per minute, that's a speed. Okay, later chapter, we'll see that's called a rotational speed or an angular speed. But think of it as the letter V. So they want you to find the speed V, but in these units. Okay, well, if things are moving in a circle and there's a V, that reminds you of this. Okay, so that means you're going to do Newton's second law in circular motion. So I'm doing that to the puck. Okay, there's the puck. Okay, so I'm applying F equal ma to the puck. So I don't need to draw the normal force. Okay, I don't need to draw that. I don't need to draw mg. Okay, I don't need to draw that. Okay, because that's happening vertically. Okay, everything in this problem is happening along the plane of the table. All right, so I'm applying. Oh, and this thing is moving around in a circle. So anywhere the puck is, it's accelerating toward the center. Okay, so that dictates my coordinate system toward the center. So the only centripetal force is the tension capital T. So I did T points inward, that's equal to mv squared over r. But what's the tension? Well, I go over to this mass, okay? This mass is not moving, okay? So acceleration 0, so there's my coordinate system. So I did F equal ma to that large mass. So tension points up, capital mg points down. So that says the tension is just mg. Okay, so I took this tension, okay, call that equation number 2, and I put it right back there. So I said substitute 2 into 1. So equation number 1 look like that. And now tension is capital mg. So right there I put capital mg. Okay. Yeah, don't cancel the m's, right? They're different m's. Solve this, cross multiply by r, divide by m, and I solve this for v. So I get a number, but that's not what they want. And they want, okay, the minimum number of revolutions per minute. So I need to convert meters per second to revolutions per minute. Okay, whoops. See, that's wrong too. That should be minute. That's a minute. Okay, all right, and we found in circular motion to do that, okay, to go from revolutions, or to go from meters per second to revolutions per minute, or vice versa, one revolution, okay, is 2 pi r meters. So I rewrote this speed, okay, and then I said in 2 pi r meters, I have 1 revolution. So that canceled out the meters. And then I said in 60 seconds, I had 1 minute, and that cancels out the s. So that gives me my number of revolutions per minute. So say about 98, okay? So anything faster, then the tension would be large, and this large mass would start moving upward, okay? Anything smaller revolutions per minute, then the tension wouldn't be large enough to keep this thing at that elevation, and it would just fall down. Okay, so in the circular motion problems, maybe in the homework, when they ask you for revolutions per minute, they're asking for the letter V, but you can't leave it meters per second. That's how you go from meters per second to revolutions. So in 1 revolution, you have 2 pi r meters.